Today we're going to continue our discussion of drawing Lewis structures and add kind of another layer of complexity, answer a few more what-if questions. So we're going to be following exactly the same set of steps that we used yesterday. For some of them we'll be adding on one additional step, but fundamentally the same process that we used in the last video. So the first thing we'll always want to do, and we're going to go through all of the steps for one example at a time today. So the first thing we always want to do is determine the number of valence electrons in our molecule. So we're going to do that using the group numbers for our elements. So we have in our first example here, NHO, we have nitrogen is in group 5, so that'll have 5 valence electrons. Hydrogen is in group 1, so that'll have 1. And oxygen is in group 6, so that will have 6 valence electrons. So this will be 5 for nitrogen, plus 1 for hydrogen, plus 6 for oxygen. Gets us a total of 12 electrons for our first example. So moving forward, the next step in our process from yesterday was to choose the central atom. So yesterday we talked about choosing the unique atom for your central atom. Here, all of our atoms are unique. In our first example, we have nitrogen, hydrogen, oxygen, one of each. We said yesterday that hydrogen can't be central, so we can kind of cross that one off. But nitrogen and oxygen are both unique here. So we need to look for something else that's going to help us predict what's likely to be the central atom. And we use a property of elements known as the electronegativity to help us predict this. So what electronegativity is the tendency of an atom to pull electrons towards itself in a covalent bond. So covalent bonds are kind of like a tug of war. We say that they're sharing electrons between two atoms, but it's not necessarily equal. Some atoms are not so nice about sharing. Some pull harder than others on the electrons. So generally speaking, there's a trend on the periodic table for electronegativity. So fluorine is the highest electronegativity of all of the elements. So this one is the highest. So that's kind of what we're comparing everything else against. Fluorine pulls harder on electrons than any other element. And in general, as you move towards fluorine on the periodic table, your electronegativity increases. So as you move left to right, you will see increasing electronegativity. And as you move closer to the top of the periodic table, so as you move bottom to top, you will also find increasing electronegativity. Always moving towards fluorine. So the less electronegative something is, the more likely it is to function as a central atom. If something is less electronegative, it's not pulling very hard on its electrons, so it's more likely to share them. It is more able to share them with other atoms, and the central atom is the one that has to share with multiple other atoms in multiple different directions. So less electronegativity is good for that. So going back to our first example here, we know that hydrogen cannot be central ever. So we're really comparing nitrogen and oxygen. So we're going to want to compare their electronegativities. Nitrogen and oxygen are right next to each other here on the periodic table. Oxygen is farther to the right, or closer to fluorine, means that it's going to have a higher electronegativity. So oxygen has a higher electronegativity, which is going to prevent it. We know that because it's closer to fluorine on the periodic table. That is going to prevent it from being able to share with multiple different atoms if there is a better alternative. So nitrogen has a lower electronegativity than oxygen, which means that nitrogen is going to be our central atom. So when you have more than one unique element, as we do here, you need to think a little bit deeper. Look for this trend in electronegativity. Whichever one is lower is usually going to be your central atom. So going forward from here, we now know that nitrogen is going to function as our central atom, and we can arrange our peripheral atoms around it. So we put nitrogen in the middle, hydrogen on one side, oxygen on the other. So remember that our target for electrons was 12 is what we're going for here. So thus far we've placed 4. So continuing onward in our process here. No, that was right. Did I cut instead of? I did. I cut instead of copied. There we go. So the next thing we're going to want to do is to fill the valence shells of our peripheral atoms with lone pairs. So remember that we're always starting with peripheral. Our hydrogen is fine as is. It only wants the 2 valence electrons, so it's good. Now we need to fill up oxygen with our next 6 electrons. So our oxygen now has 2, 4, 6 electrons from lone pairs, plus the 2 from the bond to give it the 8 valence electrons that it wants. So far we now have 2, 4, 6, 8, 10 total electrons in our structure, when we want 12. So we still have 2 electrons left to place. And they have to go on our central atom because there's no space left anyplace else. So at this point we have our 12 electrons, check, but we still have a problem here. Our nitrogen in this structure only has 6 valence electrons at this point, not the 8 that it's looking for. It has 2 from this lone pair, 2 from this bond, 2 from this bond, only gets us up to a total of 6, not 8. So when that happens, we need to add a step 6 to our process. So what we're going to do in yesterday's introduction, I drew single bonds as 1 line, double bonds as 2 lines, triple bonds as 3 lines. But yesterday we only used single bonds. Today we're going to introduce double and triple as well, but we only use them when we need to. So what we're doing to create a double bond is we're actually taking one of these lone pairs and moving it to create that second bond. So we're taking away this lone pair and we're putting it in between as a second bond. So we've increased the amount of electrons that are shared between our 2 atoms, giving nitrogen access to more. So now in this structure, oxygen still has a filled valence shell. It has 2, 4 from the 2 lone pairs, plus 2 and 4 from the double bond, for a grand total of 8 valence electrons. The nitrogen still has its 1 lone pair, but now it has 3 bonds around it, 1 single and 1 double, for 6 more electrons for a total of 8. So whenever we come across this problem here, that we've placed all of our electrons, but something has an incomplete octet, has an unfilled valence shell, that means you need to do some more sharing, that you need to create double or triple bonds. But again, we only do this when we need to. If all of your valence shells can be filled with single bonds, they should be filled with single bonds and lone pairs first. And that's why this is step 6 and why the order of the steps is important. So our final correct structure for HNO is this guy, that all atoms here have filled valence shells. And we have the correct number of electrons. So pause here and give the next one a try. Try HCN, see if you can apply those same ideas to come up with the structure. So step 1 is figuring out the number of valence electrons. So we've got hydrogen in group 1, carbon in group 4, nitrogen in group 5. So we will have 1 electron from hydrogen, plus 4 from carbon, plus 5 from nitrogen, for a total of 10 electrons. And that we'll want to keep in mind going forward. So choosing our central atom, we know once again that hydrogen is just not a contender. It can't be central ever. So we're really looking between carbon and nitrogen for which is less electronegative. So nitrogen is here, carbon is here. Nitrogen is closer to fluorine, so it has a higher electronegativity. We want the lower electronegativity as our central atom. So our central atom is going to be carbon. So since carbon has a lower electronegativity than nitrogen, carbon is going to be our central atom. And carbon is always a central atom when it is present. So, keeping in mind our 10 electrons that we're looking for, we have carbon in the center, nitrogen on one side, hydrogen on the other. So thus far we've placed 4 out of our 10 electrons. I did it again. There we go. And then in step 4, we'll fill up our peripheral atoms. Hydrogen is all set with its 1 bond, but nitrogen needs 3 lone pairs to get up to 8. So at this point, we have our 10 electrons. We have 2, 4, 6 from those 3 lone pairs, 2 and 4 from the 2 bonds, 6 and 4 is 10. So we've placed all of our electrons here already. We don't have any left to place on the central atom. So we can't actually do anything in step 5 here. We have no more electrons left to place. But you will notice that carbon only has 4 valence electrons. It has 2 bonds and nothing else, and that is not enough. It wants 8. So we don't have any lone pairs to give it, but we can create some multiple bonds. So we can take a lone pair and move it in between our 2 atoms. To create a double bond. Now, carbon still only has 6 valence electrons. So in this one, carbon now has 6 electrons in its valence shell, which is still not enough. So we can do the same thing again, and that's where we're going to get a triple bond. Oops. So we've already moved 1 lone pair to create a double bond. We're now moving a second lone pair to create our triple bond. And now carbon is involved in 4 bonds, each of which have 2 electrons in them, giving it a total of 8 valence electrons. Our nitrogen has 3 bonds containing 6 electrons plus a lone pair for the last 2 to give it a total of 8. So pause here and try the last example, CH2O. For this one, we have carbon in group 4, 2 hydrogens in group 1, and oxygen in group 6. So that will be 4 for carbon, plus 2 times 1 for each hydrogen, plus 6 for oxygen. 6 and 4 is 10, plus 2 is 12. So we should have 12 total electrons represented in our final structure for this molecule. Now, choosing our central atom, we know that hydrogen is not an option, so we're really choosing between carbon and oxygen here. Carbon is over here, oxygen is to its right, closer to fluorine. So since oxygen has the higher electronegativity, or carbon has the lower electronegativity than oxygen, so carbon will once again be our central atom. So arranging our atoms around the peripheral, we will have carbon in the middle, 2 hydrogens and an oxygen arranged around it. Again, the exact placement doesn't matter. So thus far, we have placed 6 electrons and we're looking for a total of 12. So as we fill up our peripheral atoms, hydrogen once again is fine as is, but we need to add 3 lone pairs to oxygen to fill up its valence shell with the 8 valence electrons that it wants. So we've now placed all 12 of our electrons. So 12 electrons was our target number. We've got that. So again, we have the same problem that our central atom, in this case carbon, does not have enough valence electrons. Here we have only 6 from the 3 bonds that it's involved with, and we don't have any lone pairs left to give it. We don't have any electrons left. So once again, we're pretty much going to skip over step 5 here. We have no more electrons left to place. So we're going to have to use multiple bonds. We're going to have to use double or triple bonds in order to satisfy the valence shells of all of our atoms at once. So we'll take one of our lone pairs from oxygen, move it in between carbon and oxygen, and we end up with this as our final structure.